So the first example, the length is the integral from x equals 0 to x equals 3 of the square root of 1 plus, and it's the derivative, so dy by dx, all squared dx. So this becomes the integral from 0 to 3 of the square root of 1 plus, and the derivative of y with respect to x in this case is 2x minus 2. That's all squared dx. So this is the integral now we have to compute. Now oftentimes what happens with these arc length integrals is that they can be somewhat challenging to evaluate. By the nature of the formula, they're square roots of a sum of squares. So unless they simplify down nicely, then we may need to apply a number of techniques for calculating integrals. So let's have a look at what we can do with this one. Well, the first thing we can do is substitute for u equals 2x minus 2. So du is 2 dx. We can change the limits of integration as well. Now at this stage we see it's the integral of the square root of a sum of squares. So we'll want to try see if we can get a trigonometric substitution to work. So here we'll take u to be tan theta. So du is secant squared theta d theta. And the integrand simplifies down to the square root of 1 plus tan squared theta, but 1 plus tan squared theta is secant squared. So this becomes secant theta. And so the integral becomes the integral of secant cubed theta d theta. So first we're going to use a trig identity. 1 plus tan squared theta is equal to secant squared theta. And so we can rewrite the integral as the integral of secant theta plus secant theta tan squared theta d theta. Yeah, the reason we did this identity here was, I find it easier to deal with secants if there's tangents hanging around, because then I can maybe try some sort of substitution or try some other trick to deal with it. And in doing this substitution, we end up getting that the integral splits into two integrals. One is the integral of the secant function, and that we know how to deal with. And the other one is the integral of the secant tan squared function. And that we'll have to think a little bit more about. But this first one, the integral of secant, that becomes the logarithm of secant plus tangent. And that's one we've seen in the past. And this next one, how can we deal with that? Well, I know how to integrate secant tangent. So it seems that I've got an extra tangent here that I'm having troubles with trying to figure out what to do with. So maybe let's try it by parts and see what happens. And I'll take dv to be the part I know how to integrate. And so u is the other part, which is the tan theta. And so du is secant squared theta d theta, and v is secant theta. And now the by parts is going to work if I can integrate the product of those two. And the product of those two is secant cubed. Oh, but wait a minute. The product of those two is secant cubed. That's back to my original integral. So maybe I can get an equation in that original integral and use algebra to solve it instead. So let's have a look then. So we have our integral that we're trying to find on both sides of the equation, and we can actually solve this now for that integral. So we managed to find the integral of secant cubed theta d theta. Now the one we originally wanted to find was the integral of the square root of 1 plus u squared. So the integral of the square of 1 plus u squared du is obtained by taking our integral for secant cubed theta d theta and rewriting it back in terms of u. So if we're going to rewrite it back in terms of u, we better know the relationship between u and theta. So our original substitution, u equals tan theta, so we have a little right triangle here. There's theta. Tan of it is opposite over adjacent, so that's u and 1. So this side becomes a 1 plus u squared. So tan theta is u, and secant theta, which is the other thing in the expression below that we're going to need to rewrite in terms of u, is square root of 1 plus u squared. So taking that information back all the way down here, we have that this is the logarithm of secant plus tangent, so this is u plus the square root of 1 plus u squared, plus secant times tangent, which is u times the square root of 1 plus u squared. And so all of this work was just to find the antiderivative of the square root of 1 plus u squared. And so now we can take this antiderivative and go back and finish off the integral. And this is approximately 6.125. So the length of the original curve is approximately 6.125. And that agrees with our observation when we lay the curve out flat. And let's have a look at the next example. So we're interested in the length of the curve 16y cubed plus 1 over 2y for y between 1 and 2. So the length is going to be the integral from 1 to 2 of the square root of 1 plus the derivative squared. So that's, since y is a function of x in that example, then it's dy by dx is the derivative. And so this becomes the square root of 1 plus, and the derivative of that is 1/2 y squared minus 1 over 2y squared, and then that's all squared dy. And expanding things out, and at this stage we can recognize what's under the square root as a perfect square. It's the square of 1/2 y squared plus 1 over 2y squared. And now the square root and the square can cancel off, and we get that that is the integral of 1/2 y squared plus 1 over 2y squared dy. Now the thing to keep in mind here is that the way the arc length integral is set up is it's the square root of 1 plus the derivative squared. So unless you can do a little bit of algebraic manipulation to get that square root to go away, or try some sort of trigonometric substitution, the key here is that we've got to deal with that square root. And in this example, we noticed that a little bit of algebraic manipulation to what was going on under the square root sign allowed us to recognize it as a perfect square, in which case we could get rid of the square root sign in that way. Now we can take the antiderivative. This is 16y cubed minus 1 over 2y from 1 to 2, which is 17/12. In the last example, the integral representing the arc length is the integral from 0 to 5 of the square root of 1 plus the derivative squared, and the derivative in that case is 3x squared. So this becomes 9x to the 4th dx. And now we're going to need to figure out whether we can integrate this or not. Now with a lot of these integrals, they do get complicated, as we've seen in the first few examples. The first one required a substitution, then a trigonometric substitution, and within that an application of by parts. The second example required a little bit of algebraic manipulation to get that square root to go away. We don't have to go very far to get to a situation where the function does not have an antiderivative expressible in terms of the elementary functions, the functions that we seem to be using every day, you know, trigonometric functions, logarithms, exponentials, algebraic functions. And that's what happens here. The antiderivative of 1 plus 9x to the 4th is not expressible in terms of elementary functions. So how could we see this? Well, we could go to Wolfram Alpha and ask it to compute the integral. And it comes back with an antiderivative, but the antiderivative involves this function capital F which if we look below, we see that it is the elliptic integral of the first kind. So it's a new function, a function defined in terms of integrals, not one of our elementary functions. So that's what I mean by the antiderivative is not expressible in terms of elementary functions, in terms of our trigonometric functions, logarithm, exponentials, polynomials, root functions. So what this means is we're going to need other techniques to find out what the value of this integral is. And so we would use numerical techniques along the lines of what we did in section 3.6.